Hi, welcome to the video series for differential equations. We're going to start at the beginning, which is chapter 1.1, definitions and terminology. This video series follows along with the differential equations textbook by Zill, the one that includes the boundary value problems. These lectures are being compiled into a PDF, which is created in LaTeX, and will be distributed to my courses. If you'll notice, some of the section names here don't coincide exactly with the textbook. Also, once we get into chapter 4.4-ish, you'll see that there's a few classwork problems at the end of the videos. I started this video series when we were just going to lockdown and COVID. Most of my classes, however, from this point forward will not utilize those classwork problems. Feel free to try them on your own time, but they will not be graded for those students that are taking this for my classes. Okay, so let's go ahead and get started. So we're starting off with, again, definitions and terminology. So I have found that students first taking an Intro DE course kind of get blindsided by the amount of math that's required. So I have a review list here to help you get started. Really, you just need to really focus on your calculus. Okay, the stronger your calculus is, the better you're going to be off in this class. So let's just do a brief review. Now, we're not going to get into the actual material. The material is left for you to review on your own. We're just going to kind of go over a list of the topics that are important to do well in this class. Okay. So, of course, this is differential equations. You need to know how to differentiate, right? So, understand that differentiation represents rates of change. In fact, that it represents instantaneous rate of change is going to be very important because we will talk about rates of change versus instantaneous rates of change. So, when are we doing a net change or an average rate of change versus a derivative, right? Differentiation is related to position, velocity, and acceleration. We will have many application problems where we utilize these three characteristics of differentiation in our applied problems. So it's very important that you understand the relationship between these three things. Know how to do the power rule, the quotient rule, and the chain rule, which I put down here later. Knowing the derivatives of your standard trig functions will be very, very helpful. So your sine, your cosine, and your tangent. Okay. And again, the chain rule. So I didn't put that with the power and the quotient rule, even though, again, that's one of the basic rules. Because the power rule and the quotient rule are more of a basic rule than the chain rule. And so that's why I put the derivatives of the trig functions in between the two. Really, I wrote this as it came to me, so it's not in any particular order, right? Definitely implicit differentiation, okay? So when I teach calculus, this is the form of differentiation that's generally difficult for students to understand and comprehend and to grasp. Make sure you understand what implicit differentiation is and how it works. We will be doing this a lot. Partial derivatives, they do show up in this class. We don't do them a lot, but they are present, right? So you definitely want to make sure you're familiar and okay with doing partial derivatives and your differentials, okay? Your dx, dy, and dz, okay? Also make sure you're familiar with the different forms of notation, okay? So even in a calculus class, you go over a few different forms of notation, but then when you get into, let's say, a physics course, you have an even different form of notation for differentials, okay, for differentiation. So make sure you're familiar with the Leibniz form, which is the dy dx form, okay, the prime form, which is my preferred form. Now, these two are pretty interchangeable. Well, they're all interchangeable, it's just notation, really. But sometimes some notation forms are better suited for some problems than others, okay? And you'll see that when we get into chapter 2 especially. We're going to use Leibniz quite a bit, and then we use the prime notation a lot after the fact, okay? The dot notation, which is used in physics quite a bit, is very important. So when you have a dot over your function, that generally means to take the derivative. That's used a lot when you're talking about position, velocity, and acceleration, or potentials. And then the subscript notation, where we have the differential operator with the subscript of the variable that needs to be differentiated, right? So a lot of times you see this when you're doing partial differentiation. Okay. The operator notation, which is again this operator D, it works like a function where you differentiate the function that's inside of this operator, right? Now we will use all of these notations except for the dot. You won't see me use the dot. I just threw it in there because it's important that you understand that that means to differentiate as well. Okay. Integration. Okay, so integration represents the area under a curve, so it's important to understand that as well. Although we don't necessarily use this characteristic when we go through this course, but obviously it's an inherent property, so it's important to understand that an integral represents a sum of things, basically. That is important to this course. It's the opposite operator of differentiation, right? So the fundamental theorem of calculus relates your integrals and your derivatives together. So it's important to understand that they undo each other, basically. Okay. The different methods for integration. So there's several methods, several strategies, and it's important that you are strong in your integration approaches, right? So understand the difference between a definite versus an indefinite integral, right? So one of these is bounded and one is not. Really got to make sure you're comfortable with your U substitutions. Integration by parts plays a big role in this course. Now I do integration by parts slightly different than most. I like to use the tabular method or the tableau method, which I do go over as it comes up in this class. So you may be unfamiliar with my method of integration by parts, but I try to explain it because it's not a commonly taught form in a calculus course. Okay. Improper integrals, they do show up, although very limited. It's important to understand what an improper integral is and how to calculate them. Your trig substitutions. Okay. So the method of trig substitutions is always very difficult in a Calculus 2 course. They don't show up a lot again, but it's important to know how to deal with them when they do show up, okay, because they will show up as well, right? Partial fractions. So this isn't necessarily a method of integration, but it's a tool to help with integration, right? So understand how to do partial fractions, basically how to take a single rational function and then decompose it into 2 to 3 to 4 however many necessary separate rational functions. Okay. Your series, right? We definitely cover series in this course, so it's very important that you get familiar with series. We actually have a portion of this course in chapter 6 where I do have a separate video where we do a review of series because there's just so much to discuss and we use it quite a bit. But make sure that you take the time now to get slightly more familiar with your series and to review. It will help you out down the road later on. Okay. So your tests for convergence and divergence. There's several tests for convergence, several tests for divergence, right? So it's very important to get familiar with those and when to use them. Understand what your interval of convergence is and how to calculate it. The arithmetic rules for combining series, right? How do I add series, factoring out constants, changing indices, things like that, right? So adjusting the index of a series. And how to do a power series expansion, right? So Taylor series expansion, power series expansion, Maclaurin series expansion, those are all pretty important as well. Understand how to integrate and differentiate a series, which is just like integrating or differentiating a polynomial, really. So those are all things that you should be familiar with as you go through this course. Okay. So let's talk about DEs, right? So a differential equation, which we like to refer to as DE because we're math people and we like to use shorthand notation for everything, right? So when you see DE, I'm referring to a differential equation. This is an equation that contains derivatives. That's basically it, okay? So derivatives, as I said before, right? Understand that it represents rates of change. You use a DE to represent anything that has changing values, right? Things like traffic, weather, rocket science, population, things that change over time need to be modeled with a differential equation, okay? The solution to a differential equation is a function, right? So this is one of the things that's kind of hard for people to grasp for a DE course. You are not solving for a variable. You're not trying to find x equals 3, right? You are trying to solve for a function that satisfies this differential equation that you have. So your solution will be a function or a family of functions. It can be an infinite amount of functions that satisfy this. So you're going to either look for a specific function or a general form of a function that can be manipulated to fit whatever conditions that you need to set later on down the road, okay? So again, the function we're trying to solve for is y, that satisfies the DE, okay? We're going to talk quite a bit today about categorizing differential equations. Now there's many different ways of categorizing them. We're going to go through pretty much all of them right now, right? One of the main ways is as ordinary differential equations. So that's the focus of this course, is to focus on ordinary differential equations where you are using ordinary functions in order to find your solution to these DEs. It has a single output, or I'm sorry, single inputs or multiple inputs. They're they're our standard way of dealing with a differential equation, right? And we call those ODEs for ordinary differential equations, okay? The next that we have is partial differential equations, and those are higher order equations. So PDEs are something that you would see in a separate class. There are other community colleges that do cover ODEs and PDEs in this exact course. However, we're going to focus on ODEs. We may, if we have time, get to one or two PDEs just to discuss them and see an introduction to, higher level math. But PDEs are where the fun is at. Okay, so all the interesting things you want to study, quantum mechanics, things like that, are going to have to do with partial differential equations. Okay. Another way of categorizing a DE is by its order. The order of a differential equation is similar to the power of a polynomial. Okay. So the order is the highest derivative that's present in the equation, right? So just like if you have a polynomial, you classify a polynomial by the highest power that is there, right? This is a 3rd degree polynomial. This is a 6th degree polynomial, right? So the degree of a polynomial is the highest power. The order of a DE is the highest derivative that is present. Okay, so here are a couple examples. A first order differential equation should not have anything higher than a first derivative present. Okay. A second order DE will have a second derivative present in the equation. Okay. So what this is basically saying for this first order here is that if I take a function and I differentiate it and I add it to the original function, I will get out 2x, right? The second order here says that if I have some function y and I take its second derivative and I subtract from that its first derivative and add to that 3 times my function, I will get 3x, right? So here I'm doing manipulations, arithmetic, on my function that forms a solution for my DE, right? So again, for a DE, our solutions are a function, right? I'm looking for a function that satisfies this. Okay, and so forth and so forth and so forth until whatever order it is that I need, the nth order, I guess we would say. Okay, so that's one way that we classify them, right? As ODEs and PDEs, or by their order. That's actually the main classification, right? The next way is by their linearity, right? We have linear and nonlinear DEs. So a DE is linear if the highest power that shows up of y is of degree 1. Okay, so if I had, let's say, y squared, y double prime, that would then be a nonlinear. So both of these are examples of linear DEs because there is no degree of y that is different than 1. Okay, so an example of a few nonlinear DEs is y prime minus 3xy equals x. Okay, so the reason that this is nonlinear is because I have a function times its own derivative, right? So this term is the term that makes it nonlinear, right? The second derivative of y minus y squared equals 3. It's not the second derivative, but it's the y squared term that makes this a nonlinear DE. Okay. So we can also classify DEs according to their homogeneity, right? So we have what's called homogeneous equations and non-homogeneous equations. So again, just to review real quick, so far we can classify as ODEs versus PDEs, classify them according to their order, or classify them as linear versus non-linear. Okay, so again, these are two nonlinear. Both of these are linear forms, right? So homogeneity is another way. Basically, if we put a DE into standard form and it's equal to 0, then it is called homogeneous, right? So example, we don't have one yet. Okay, so standard form means that all of the y terms and their derivatives are on one side of the equation. Okay, if it is not homogeneous, then it's called non-homogeneous, right? So an example, here I have my DE, it's in standard form. All of my y's and its derivatives are on one side. On the other side, I'm left with 0. That means that it is homogeneous. Okay. Here I have my same diffeq, right? But it's not equal to 0. All of my functions of y and all of its derivatives are on one side, and on the other side it doesn't matter what's left over. And in this case, it's a non-zero term, so it's non-homogeneous. Even if I were to take this and move it back over, it would still be non-homogeneous because this doesn't have any powers of y in it, right? So all of these previous forms that we had here, these are all non-homogeneous as well, right? My DE with its derivative and its functions all on one side is equal to a non-zero term, non-zero term, non-zero terms, right? So all of these are also non-homogeneous. So lastly, we can classify a DE based on its conditions. Okay, we have what are called initial conditions and boundary conditions. If we have initial conditions, then we call it an initial value problem, right? We are given an initial set of values that are needed for our solution function to satisfy. We call the initial value problems IVPs. Okay, an IVP is a DE that has some set of what we call, again, initial conditions. Okay, boundary value problems, which we call BVPs, okay, have conditions set on the outer boundaries of their DEs. Now we'll get into all this a lot deeper throughout the course, obviously, but just give you a quick example of what this means. So initial values make sense, right? So maybe I have a solution to a DE and I require that my function starts off with an output of 5, right? So for instance, maybe I have a differential equation that models a ball's flight through air, right? So we have obviously several changes in velocity, changes in position, and we have acceleration due to gravity. And maybe the ball has an initial height of 5 feet, right? So the initial value is 5. So I have an initial condition that's necessary on my solution function, okay? A boundary value problem is a little bit different. This has conditions on the boundary. For instance, maybe I have a rod, and on this rod, this metal rod, I have one end that is submerged in ice water and another end that is being held to a candle. Okay, so I have an initial condition then of 0, right? And or negative 32 if we're using Celsius. If we're using Celsius, the initial value would be 0, and the boundary value at the end, at the length of this rod, would be at 100, right? Okay. So an IVP again is a D with conditions placed on the initial values of any solution or solutions that may be viable. A BVP, boundary value problem, is a D with conditions placed on the end boundary of a potential solution. So if there are conditions on the initial values and end boundary values of a solution at the same time, then we classify that as a BVP. So again, if I have initial conditions and boundary value conditions, BCs is what we call them, boundary conditions, then that's a BVP. It's a boundary value problem. But if I only have initial conditions, then I'm an initial value problem. Okay, so again, one more time. There's only initial conditions, it's an IVP. If there's initial conditions and boundary conditions, it's a BVP. Okay. So example, so let's say that this is the diffy Q that I would like to find a solution for, and it has an initial condition of 1 and another condition that the first derivative at the same point is -1. That's an IVP. Okay. If I take the same equation and I put on that at y of 1, I get out 1. And same thing with this derivative. Then that's a boundary value problem, right? Because now I'm specifying something at the end. Now, an initial value problem does not always have to be centered at 0. Okay, but if you have initial condition for the solution and its derivative, they need to be at the same point. Okay, so for instance, if my initial condition was at 0 here, but for the derivative was at 1, then that would be a boundary value problem because this would specify an initial condition and this would be a specification for the boundary value. Okay, so if I'm doing initial conditions for y and all of its derivatives, they all need to be centered at the same initial point. Same is true for boundary conditions. I can't set a boundary condition at 1 and a boundary condition at 2 for something else, for one of the derivatives, because then that's saying that my boundary is not at 1 or at 2, it's somewhere else, right? So whatever my boundary is, my function condition, my solution condition, and any of its derivatives need to be at that point as well. And again, that's not super necessary. We'll get into all of that later on down the road when we get into boundary values. Okay. So here you can see I have a function with a mixture of an initial condition and a boundary value because they are at different points. Okay, so this would be considered a boundary value problem. Okay, so we can put all these classifications together whenever we want to describe a differential equation, right? So when we look at what's given to us, that's how we specify what we have. So let's look at a couple of examples. Okay, here I have a second order non-homogeneous differential equation. Okay, and it's an ODE, which I don't really have to specify, but you know, it's nice to be able to specify that as well. So it's a second order non-homogeneous ODE. Okay, and it's also nonlinear. I guess I skipped that part because I have a nonlinear term as well. Okay, so a second order non-homogeneous nonlinear ODE, and it doesn't really matter what order I put these classifications as long as I'm putting all the classifications. Right? For instance, I could say it's a nonlinear non-homogeneous second order ODE. That's fine. It doesn't have to be in any particular order, except for whether it's an ODE or PDE is generally the last thing that you specify in general. Okay, I obviously could say it's a non-homogeneous nonlinear ODE of second order, right? So it really is up to you how you want to specify. Okay, here this is third order. It is homogeneous, and there is no nonlinear terms. Okay, so this is a third order linear homogeneous ODE. Okay, here, okay, obviously we have some partial derivatives, right? So the function u in terms of the partial t is going to be equal to some constant alpha times u to the second partial of x, u and partial second of y, and u partial of z, right? So there's no nonlinear terms here, okay? And everything has second derivatives, right? I differentiate this twice in terms of x, twice in terms of y, twice in terms of z. So it's linear, second order. If I put all the u stuff on one side, I'd be left with 0 over here. So it's homogeneous and it's a PDE. Okay. All right, something of this form. Okay, I got my y's. There's no nonlinear terms here because this nonlinear term is in terms of x. This nonlinear term is in terms of x, so it has nothing to do with the solution function. So it's non-homogeneous. It's first order. It's linear. Looks like I have an initial condition here, right? So it's a first order linear non-homogeneous IVP. Okay. So now let's talk about solutions. Right now we're not going to talk about finding solutions because that takes a little bit of time. We're just going to talk about how solutions behave a little bit. Okay. So if I want to verify that something is a solution, right? If I'm given y equals this is a solution to this DE, basically what I need to do to verify that is I take my differential equation, or I take my solution and I find the derivatives necessary and I just plug it back into my equation. Okay. Now normally these solutions that we have to our DEs will be a family of solutions. Okay. Once we put initial conditions on our differential equations, it'll help us to narrow down to a single particular solution. Maybe I shouldn't say particular solution. We reserve that name for something else. But it helps us narrow down to a specific solution. Okay. If we don't have any initial condition set, generally we have an infinite number of solutions that satisfy our DE. Okay. Now, when that's the case, in this general sense, we're looking for the general form of our solution. Okay. So again, infinite amounts of solutions that take on the same basic form, right? So initial conditions allow us to narrow down a specific solution to a DE. We cannot say the same thing for BC's boundary conditions. Okay, boundary conditions can still have an infinite number of solutions that satisfy the DE and those conditions that are set. So let's talk about how to do this. Okay, so let's consider the function y equals e to the 3x cosine of 2x. And the DE, y double prime minus 6y prime plus 13y equals 0. Now, we're going to verify that this is a solution, and we're going to do so by finding the first derivative, finding the second derivative, and then plugging those into this equation. Okay. Now, when I ask you to do this on an exam or homework or anything like that, I need to see all of the work. Okay. So, for instance, something that will get you marked off very quickly is if you take this derivative, you take this function, if you differentiate it once and differentiate it twice, set it all equal, and then just tell me it's equal to 0, that's not you verifying, right? You didn't actually cancel things out. You need to show me all of your work. I'm very, very particular in my classes about showing all of your work, especially for the semester that I'm creating these videos in. We're still in the middle of COVID. And so if I don't see all of your work, I'm really just going to assume that you are using some outside source for your solutions, which is not going to bode well for your exam scores, right? So make sure you are writing as much material as possible for me to be able to follow along, okay? At least as much as I am showing you in these videos. So to verify whether or not y is a solution, we're going to need the first and second derivatives, as I said before, okay? So it's e to the 3x cosine of 2x. So this is one function times another function. So we're going to use the product rule. Okay, so again, hopefully you guys have reviewed a little bit as we go through this. Okay, now I don't think I've said this yet, but the best way for you guys to watch these videos is to pause and take notes as we are using these. Now I know for my classes that I have write-ups available, which is really the script that you're looking at now. But if you want to get the most out of this, you should really handwrite your notes as well. Go through these problems along with me. When I do an example, maybe you should pause it and do that problem yourself, and then go ahead and press play on the video and see if you get the same results that I get. Okay, but it's very, very, very important that you watch these videos with a paper and pencil. You should 100% be taking notes as we go through this process. Okay, so I need to find my first derivative. So I'm going to be using the product rule here. So differentiate this times this function plus this times that derivative, right? So 3e to the 3x times the second function plus my first function times the derivative of the second function. Okay, so here we got the chain rule, since cosine of 2x is a function inside of a function, right? So when you do the derivative of cosine, the way that I remember it is that c means you change signs, right? So you get a negative sine 2x. Okay, and there we go. Okay, so that's our first derivative. So now when we do my second derivative, we're going to do the same thing, but we're going to do the product rule here and the product rule here, right? So I'm going to differentiate this, which is going to give me 9e to the x. And then this function stays the same, plus 3e to the 3x, okay? And then the derivative of this, which gives me that negative 2, and then the cosine turns into a sine of 2x, okay? Then I do the same thing here. This will become negative 2 times a 3e to 3x times sine of 2x. And then I will have the derivative minus 2e to the 3x times s means stay the same, so it does not change signs. So this turns into a cosine 2x. Okay. Okay, so I got all my derivatives. So let's go ahead and simplify these things down since we're going to be plugging them into our DE. So obviously this is 6e to the 3x minus 2e to the 3x sine 2x. And then here we have some things that we can combine, right? So this is a cosine 2x term and another cosine 2x term, and the e portions are the same. So I have 9 here, and I'm subtracting 2, so I should get 5. Then these two terms are the same, so I have negative 6 and negative 6, so that should be 5 e3x cosine 2x minus 12 e3x sine 2x. Okay, this is what we got, right? So now we're going to take these things, we're going to plug it into my DE. Okay, to our original. So this was our original. So we're going to take y double prime minus 6y prime plus 13y and check to see if it is 0 or not. Okay, so this is a very, very important process here because theoretically, well, not theoretically, but basically this means you can check every single one of your problems. Okay, so if you're ever like, I don't really know if this is right or not, take your solution and plug it back into your DE, right? If you don't get out what you're supposed to get out, then you messed up somewhere and you know you can go back and fix things, right? So you can always verify your work in this class, right? Just like in an algebra class, there's always something you can do to check to see if your work is correct, okay? So let's go ahead and plug these in. So again, I have very long equations. They're not actually going to fit on this page, so you might see that it looks a little weird here. And that's just because of the format of the program that I wrote it in. So I'm going to take y double prime. So you see here, I have it in parentheses. I'm going to minus 6 of these things. Okay, so minus 6 times my y prime term. And I'm going to add that to the original function, 13 of my original functions. Okay, so what we can do is we can just kind of pull out the e to the 3x. You can see here that it's a common term on everything, right? It's e3x, e3x, e3x. The only thing that's really changing is the coefficients and whether it's cosine 2x or sine of 2x. So we'll pull out the e to the 3x and then we'll collect our coefficients. Okay, so that's a common term. So if I'm taking the cosines first, I have 5, right? Here I'll have negative 18, and here I'll have 13. Okay. For my signs, I'll have negative 12. I will have a positive 12 and none here. Right? So this is 0. 5 and 13 is 18 minus 18 is 0. So I basically have 0 plus 0, which is 0. Okay. So this was a very specified solution. Okay. This e to the 3x cosine 2x that we have here. Okay. That was not a family of solutions. So a family of solutions of that form would be if I had an unknown coefficient multiple, right? So if I were to do the same thing with y equals c1 e to the 3x cosine of 2x, it should work as well, right? So if I were to multiply this by any constant term, negative 1/2 times pi times square root of 2, and I did the same thing to it, it should work. And that's why this general form here gives me a family of solutions, because there's an infinite number of possibilities for what this actual function could be, right? Here in this example that we had, I used c1 was equal to 1, right? And c1 was equal to 1, that's why there's no c1 term here, or no constant multiple. So let's go through this really quickly, okay? So as long as c1 is a constant, meaning that c1 is an element of the real numbers, you're going to see this notation a lot in this class, okay? I use a lot of mathematical shorthand, so if you had me before, you're familiar with this. If not, you will get familiar with it, right? So if I'm an element of R, that means I'm a real number. Again, pi, square root of 2, 3/2, 12, any real value, okay? So if I had this, I would get the same result. So the difference again is that this form represents a family of solutions which all vary by an amplitude, right? I'm multiplying my solution by a constant multiple, so it will grow it in amplitude or it'll shrink it in amplitude, right? They all satisfy our DE, whereas this represents a single solution because it's not a constant multiple, a variable constant multiple, right? It's a single solution. This is the solution. It's not some multiple of that, okay? So, in fact, if I took y equals e to the 3x cosine 2x, this specific solution here represents a solution to my DE, okay, that satisfies the initial condition of y of 0 equals 1 and y prime of 0 equaling 3. So if I specify some initial conditions, I can whittle down my general solution down to a very specific solution, okay? So once I put some conditions on it, I can go from a family of functions to ideally a single specific solution that satisfies those ICs, okay? So example, if we just run through this real quick, right? If this was my y, my first derivative would look like this. The only difference is that it's the exact same thing here, except there's the constant c1 in each term, right? Still 3e3 cosine 2x, but a c1, right? It's the same form, but there's a c1. And my second derivative would be the same thing, 5e3 cosine 2x, 5e3 cosine 2x times that constant multiple, and then the same thing here, minus 12e3 sine 2x, minus 12 times that constant multiple, e to 3x sine 2x. And if I were plugging into my DE, okay, would be the same thing. I would have a constant term of c1 e to the 3x everywhere, right, just like I did here, that I can pull out, and I still end up with this same internal portion here, which is 0 plus 0, which is just 0. Okay, so now if we were to look at this as a graph, this is what this would look like. I grabbed several potential solutions, all varying by an amplitude. Okay, so obviously here I'm multiplying by maybe c1 was equal to 1/4, maybe 1/2. This one is probably times 2, times 3/2, times root 2, times pi, whatever. Okay, but our particular solution, our specific solution that goes through the point 0, 1, is that solution that I have here. Okay, this y equals e to the 3x cosine 2x that I says satisfies this initial condition if I were to have specified that. Okay, so once I choose some initial conditions, right, I can narrow my infinite amount of solutions down to one specific solution that models whatever it is I need to model. Okay. So now let's talk about interval of existence. Okay. The interval of existence of a solution is the same as the domain over which that solution satisfies whatever these initial conditions or any conditions that I have of the DE. Okay. For example, let's say that I have a differential equation that has a solution of y equals 1 over x. Okay. Now, if I graph 1 over x, the solution function, it's in two discontinuous portions. This is a non-continuous function. Okay. Let's say that I have a condition that I need my function to satisfy this point, 1, 1. Well, if that's true, then the portion of this that works is this portion that's in quadrant 1. This part does not work as a solution because it doesn't satisfy my condition. So I would not say that this is my solution. I would say y equals 1 over x over this specific interval from 0 to infinity, not including 0, is my solution, right? This would be my solution at that point, right? And the interval of existence is from x from 0 to infinity, not including 0, obviously not including infinity because it's infinity, right? So now I would have a interval where my solution works for a solution for my function.